So, this is an introduction to organic chemistry. Originally, organic chemistry was known as chemistry of carbon compounds, and I'm going to explain that in a few minutes. Previously, scientists did not believe that you could synthesize compounds of organic chemistry in the lab. So, what they normally did was they consulted living organisms or organisms that were formerly living for compounds such as urea, vitamins, antibiotics, sugars, and proteins. So, this was a long held tradition up until 1828, where a chemist known as Frederick Wooler synthesized urea accidentally in the laboratory. What he did was that he put ammonium cyanate into fire and then heated it under extreme fire. And then he found out that the byproduct he got was urea. So this discovery, a very groundbreaking discovery, changed the notion that scientists had previously that organic compounds could not be synthesized in the laboratory. So he sent them to work, and then they studied a lot of compounds. So what they considered was they did studies on the remains of living things or organisms that were formerly living. So what they studied a lot was about petroleum and then coal. And then they found out that petroleum and coal had one thing in common. They contained a lot of carbon compounds. So they then changed the name from organic chemistry to chemistry of carbon compounds. But that definition is a warped definition. It is warped because, for example, we have a compound like potassium cyanide. It contains carbon, yet potassium cyanide is not an organic compound. We also have a compound such as sodium carbonate. Sodium carbonate contains carbon, yet sodium carbonate is not an organic compound. And the popular one is carbon dioxide. Carbon dioxide contains carbon, yet carbon dioxide is not an organic compound. So they studied a lot about all the elements that are in the same group as carbon. For example, silicon. They also did studies on silicon, and they also studied tin, and then they studied lead. And they found out that all the elements in the group 4 of the periodic table are able to form a lot of chains of compounds with themselves or also with other elements. So this forming of long chains with themselves is what is popularly known as catenation. Now, some of the products that we get from organic compounds are polymers. We also get dyes. We get plastics, pesticides, and then food additives. These are all products that we get from organic chemistry. But in the study of organic chemistry, it is based on logical principles and also deductive reasoning. So what happens is that you may not know every organic molecule, but those organic molecules have been classified according to their functional group. So if you know the properties of a certain functional group, it doesn't matter the molecule that you are given. That molecule will exhibit characteristics that are similar to the functional group to which it belongs. This then leads us to discuss about functional group chemistry. So let's consider some functional groups. So the simplest functional group is the alkenes. The alkenes are when you see a carbon in a straight chain with another carbon, then you are dealing with an alkene. Or a carbon in a straight chain with a hydrogen, then you are dealing with alkene. But the next one is the alkenes. The alkenes are carbon in double bond with another carbon. And then the next one is the alkynes. Alkynes are carbons with in triple bond with another carbon. We also have this functional group known as the arenes. The arenes are normally benzene rings, and they normally form the aromatic compounds. So these are the arenes. Then we also have alkyl halides. Alkyl halides. Now a halide is an element that belongs to the chlorine, the iodine, and then the fluorine family. So the alkyl halides are normally like this. The alkyl halides are normally carbon bonded to a halogen. I have used X to denote halogen. The halogens are normally fluorine, chlorine, and then we also have iodine. These are the frequent ones that we normally encounter in organic chemistry. Then we also have the alcohols. The alcohols are a carbon that is bonded to an OH group. So anytime you see a carbon bonded to an OH group, then you are dealing with an alcohol. Then let's compare these functional groups. We also have ethers and esters. Some of them are similar. We need to differentiate between them. So an ether is a carbon in single bond with an oxygen, which is also in a single bond with another carbon. Nonetheless, an ester is a carbon that is in double bond to an oxygen and in a single bond to an oxygen again, which is in a single bond to another carbon. So this is the difference between an ether and an ester. We also have aldehydes, an aldehyde and then a ketone. So an aldehyde is a carbon that is in double bond with an oxygen, which is bonded to a proton. However, a ketone is a carbon which is in double bond with an oxygen, which on each side is bonded to a carbon. So this is the difference between a ketone and a carbon. For the ketone, the carbon bearing the oxygen is bonded to two other carbons. However, in aldehydes, one of the carbons are substituted with a proton. The next one we have is an amine. An amine is a carbon that is bonded to a nitrogen. This is the amine functional group. Then, apart from the amine, we also have the imide. The imide is a carbon that is doubly bonded to an oxygen, then bonded to a nitrogen. So this is the difference between the amine and then the imide group. In the amine group, the carbon bonded to the nitrogen is not in any double bond to an oxygen, whereas it is the same in an amide. Then the next one we talk about is nitriles and then the nitro. Nitrile and then the nitro. Nitro is a carbon that is bonded to an NO2 group. And then a nitrile is a carbon that is in triple bond with a nitrogen. The next group are the acid chlorides. And then an acid chloride is a carbon that is bonded to in double bond with an oxygen, which is bonded to a chlorine. This is an acid chloride. Then we have acid anhydride. Acid anhydride. So that functional group is a carbon in double bond with an oxygen, which is bonded to another oxygen, and this oxygen bonded to a carbon which is bearing a double bond to an oxygen, and then they are linked together. So this is an acid anhydride. And the last group is the sulfur groups. So with the sulfur groups, we have a carbon bonded to a sulfur, which is bonded to a hydrogen. This is called the thiols. This is a thiol. So thiol. Then the next one is a carbon that is bonded to a sulfur, which is bonded to another carbon, and that is a sulfide. And then the last one is a carbon which is bonded to a sulfur. Carbon bonded to a sulfur, with the sulfur in a double bond to an oxygen. And this sulfur again bonded to a carbon. And this one is called the sulfoxide. The sulfoxide. So these are some functional groups that will be of a lot of help in our journey in organic chemistry. So let's solve this question. Wisanin was first isolated from a Ghanaian medicinal plant, Pipa guineense. Its local name is called Osorowisa. Identify the functional groups in Wisanin. So if you look at this, you see that just on the first look, you can identify an alkene here. So let me label this as A. So A is an alkene functional group. And then apart from A, you can identify this functional group, which will represent as B. The functional group B is called an arene. So there's an alkene and arene. When you see a benzene ring inside an organic compound, it's called an arene, aromatic compound. Then apart from that, you can see this. There's an extension here which I forgot. So there is OCH3 at this part. And then this is an ether group. So let me label that as C. So C is an ether. And then you can see this functional group, nitrogen that is bonded to a carbon in a double bond with an oxygen. So let's label this as D. And that is an amide group. So this is an amide. In a laboratory, the compound below was isolated and identified as methyl 1-phenyl ethyl N-phenyl propion amido piperidine 4-carboxylate. Circle all the functional groups present. So you see that just at a glance, you can find an arene group here. So let's say this is A. So A is an arene group. And then apart from arene, you see this is an amine. Carbon bonded to a nitrogen is an amine. So this is B. So B is an amine. And then apart from that, you can see this functional group here. A carbon in double bond to an oxygen, which is in a single bond to an oxygen and bonded to a carbon. And let's say that is C. And so C is an ester. And we can see this functional group here. Carbon in double bond with an oxygen, which is in a single bond with a nitrogen. So let's say that is D. And D is an amide. So these are the functional groups on this compound. We have an arene, an amine, an ester, and an amide. The compound below is a derivative of a natural product, aflatoxin, B1. Circle and name all the functional groups present in the compound. So you can see that just at the glance, we can find an arene group here. The arene is the simplest to always find. So A is an arene group, and then you can see that this is an AB, and then B is an alkene. So we have an alkene group there. Then you have a carboxylic acid also here. So C is a carboxylic acid. Then apart from a carboxylic acid, you see carbon bonded to nitrogen. So carbon, this is a methyl group. It is bonded to a nitrogen, and that is an amine group. So this is an amine. So let's say that is D. D is an amine group. And then let's look through to see if we can find another. You see there's a carbon here that's in double bond to an oxygen, which is bonded to another oxygen, which is bonded to this carbon. And let's say that is E. And that E is an ester. Let me cancel it. Ester. So you can see that we have here carbon bonded to an oxygen, and with the oxygen bonded to another carbon. So let's say that is F, and that is an ether group. So F is an ether. And then you see sulfur that has been sandwiched between two carbons, and that is what? A sulfide. So FG. So G is a sulfide. Circle and name all the functional groups on the structure below. So let's try and see if we can find some. Nitrogen, that is bonded to carbons. So you can see that. So let's denote that as A. A is an amine group. So this is an amine. And you can see an OH. Carbon. Okay, so here you can see a carbon that is bonded to an OH group. So let's say that is B. And B is an alcohol. And then apart from that, you can see that we have an alkene here. So this is C. C is an alkene. Then our arene groups are here. So D. D is an arene group. Then from here you can see a ketone. Carbon that is doubly bonded to an oxygen, which is bonded to carbons on each side. So let's say that is E. E is a ketone. The last one here is this functional group, F. And this functional group, carbon in double bond to an oxygen, which is bonded to a nitrogen. And so F is an amide. So these are the functional groups that are on this compound.